Okay, can you hear me? Okay. So thank you, Marc-Antoine. So I'm very happy to be here, and I would like first to thank the organizer of this conference to accept my talk. It's always very special to present something during your first conference, especially when you're a first PhD student like me. So I would like to present the work I'm doing at KU Leuven with my colleague Azzurra Bighioli, and with the help of all the co-authors that you can see here. So we are working on the instrumentation of the Hi-5 instrument at KU Leuven, and especially the warm optics design and the test bench of the instrument. Is it working? Yeah, perfectly. So you can see that the main objective of our work is to find a way to inject the four beams of the VLTI in the four inputs of our integrated chip. So you can see the sketch that Denis just presented you earlier. So you can see the four inputs, 0, 1, 2, and 3, that corresponds to the four telescopes of the VLTI. And then you have the double stage interferometer to create the Nulling outputs that we use for exoplanets detection. And so as you can see, the challenge is that we have four beams from the VLTI with a diameter of 18 millimeter and a separation of 240 millimeter. And we need to find a way to inject it into four inputs with a few micrometer diameter and a separation of only 125 micrometer. In this field, you usually have two options. The main one is the fiber injection setup that is used on the instrument like IOTA, Pioneer, and Gravity, for example. So the idea in these instruments is to attach the four optical fibers corresponding to the four telescopes of the VLTI and to attach it directly to the chip. Then you have a very compact and stable system. Unfortunately, for the Hi-5 instrument, we have three main requirements. First, we need to work in the mid-infrared, in the L band. Then we also need to have a control of our polarization between the four beams. And we also need the chip to be in the cryostat because we work in the mid-infrared. And when it comes to fiber technology, these two constraints, like working in the mid-infrared and wanting to control the polarization. So if we want to attach the optical fiber to the chip, they need to be resistant to low temperature in the cryostat. And unfortunately, the fiber technology today is not suited for this. So we have to use a direct injection system that is used, for example, in the glint that Marc-Antoine just presented earlier. So the idea is just to use basic optics like lenses to focus the beams in the waveguide of the integrated optics. In interferometry, and especially in Nulling interferometry, we also have to take into consideration four constraints when designing our optical system. The first one is obviously the alignment. You want your system to be very optimized. You want the alignment to be as good as possible. So for this, we will use tip-tip mirrors and retro-injection system. I will talk about this later. You also have the polarization. This is very important for Nulling efficiency. You want the polarization of your four beams to be as close as possible. So for this, you want to have a design that is very symmetric and also mirrors with the smallest angle possible. Thirdly, you have the phase control system. Obviously, you want to control the phase difference between your four beams. So for that, you are using mirrors, OPD mirrors. And finally, you also want to be as achromatic as possible. So for this, you only want to use reflective optics in the warm optics design. And also you want to use chromaticity compensators. I will mainly talk about the alignment because this is the core of my work since the beginning of my PhD. So here I show you the current Hi-5 design we have. So you can see that the four beams of the VLTI are first going through a polarization and water vapor control system. And then the four beams are entering the injection system here that I will show you later. So the injection system is focusing and injecting the four beams in the optical chip, in the integrated chip that is in the cryostat here. And after the chip, you have all the spectrograph design here that is not in Leuven. The spectrograph is designed in Liège. All right, so I will give more details about the injection system. So you can see that the four beams of the VLTI are being focused on the chip by four parabolic mirrors. The 4 parabolic mirrors have the same angle and same focal length, because I told you earlier that we need to have a system that is as symmetric as possible for polarization purpose. Then you have the slicer that is directing the 4 beams towards the photonic chip. And between the 2 of them, you have 4 tip tilt mirrors here that will have 2 degrees of freedom to optimize the injection. So basically, each of these mirrors will be used to align the pupil plane with the cold stop of our system. And just after the slicer, you have this system that we call a telecentric system. If someone is interested, maybe you can ask the question, what is a telecentric system? Maybe I won't have the time. So we are using 2 lenses to inject the 4 beams in the optical chip. And this is a very critical part of our system, very critical. We need to make a tolerance analysis of our system here to know how precise we need to be and the precision of the system we need to build. And so for this, we are simply moving the chip combiner transversally with the delta X and longitudinally with delta Z. And we are simulating how much power we are losing with a slight misalignment. And so you see that for a transversal misalignment, if we want to keep a power efficiency above 50%, we have to reach a precision of 16 micrometer. But for a longitudinal misalignment, we can have a precision for the, again, to have a power above 50%, we can have a precision of only 500 micrometer. So this is obviously the transversal misalignment that is the most critical in our system. Luckily, we have a possible solution against this. If we are trying to glue the last lens of our system to the chip combiner, and if we are doing exactly the same study as before, then we obtain a precision that only needs to be 160 micrometers. So we have a factor 10 precision less on our system. So it makes the system far more robust. But we still have to test it because we are not sure if this solution is feasible in a cryostat. Then, to make the alignment of our injection system even easier, we want to implement a retro-injection system similar to the one that is used in the Pioneer instrument. So we are using a black body source to send light in the cryostat and then send light back of the chip combiner. So then the 4 inputs of the chip are becoming sources of light. And then we can try to align the 4 beams of the VLTI with the 4 beams coming from the chip combiner and try to align them to make the alignment of our system easier and more effective. On another topic, so we leave the injection system, we want to have a test bench in our lab to test our instrument, because obviously you cannot go to Chile with an instrument you haven't tested and try to see if it's magically working. We have to simulate the 4 beams of the VLTI in Leuven in our test bench. So for this, we are using a parabolic mirror here that is here to collimate a beam. And then we are using a subaperture mask to create the 4 beams of the VLTI, and then a set of optics that we use to align with the right separation and the right height. So as you can see, we made this system in the lab. This is the system you can see on the left. On the top right, you see what is the result in visible light. So you can see that the 4 beams are visible in the right separation and the same height. And I wanted to show you the result in the mid-infrared when we switch our source to the black body source, and we are watching the result in our infrared camera. We see that we actually have enough signal to noise ratio to align our system I was confused. Okay, thank you. To align our system and optimize the beam at the end. So here's a summary of all the things I told you about. So at first, I told you about the injection system we have. So you saw that how we were focusing the 4 beams of the VLTI in our integrated chip. I also demonstrated to you how a glued lens at the end of our system is more robust for against the possible misalignment we may have. but we still need to test this solution. Secondly, I showed you a few options we have to optimize the alignment of our injection system. So for example, with the retro injection system. And finally, I also showed you the test bench we're working on in the lab. And for example, the 4 beams of the VLTI simulator. In the future work we envision, we first need to work on the alignment more of our system. So for example, we will test this idea of retro injection system and see if we have enough signal to noise ratio to actually do it. In theory, this should be possible. We need to continue the tolerance analysis of our instrument. And for example, we need to test how much power we lose when we rotate the chip combiner. And as I said a few times, we need to test the glued lens solution. Also, we need to implement the 4 RPD mirrors for phase control, as I told you earlier. And finally, we also need to work on the polarization and see what is the impact of the possible difference of polarization between the beams. What is the impact of the nulling efficiency of our instrument? And I will stop there. So thank you for your attention, and I will answer the question you may have.
So, is there any question? Okay, there is one online. So you mentioned that the injection is very sensitive on polarization. Do you need to take extra care for the polarization of the 80s, which is known to be different for the 4 telescopes?
Yes, well, that will be the purpose of the polarization control system here. The polarization control system will be here to tackle with the problem of polarization we may have beforehand. The problem also with polarization is especially after the polarization control, because the possible polarization difference we may have after the system of control can be a problem. I hope I answered the question.
Yeah, and another question from Narcy. How much coupling efficiency is aimed considering your science goal?
The coupling efficiency, well, we are aiming for the maximum, so 81%, which is the maximum efficiency we can have. So we are aiming for this.
Okay, very question in the assembly. Have one. So when you compare the different injection with the fibers glued to the chip or direct injection into the chip, for the fibers, you mentioned that one issue was the polarization in the mid-infrared. So what do you mean about that?
Oh, yes, it's because, where is it? Yes, so as I said, we need to, potentially these fibers to inject will be after the polarization control system. So as I told, we need to be sure that the polarization between the 4 beams is the same. And the problem is, a mid-infrared fiber, we are not sure if after the polarization control, the polarization will stay the same. We're not sure of that. And so that's one of the problems for the fiber injection solution.
Okay. Well, we can. Thanks again, Germain.
Thank you.